In this section, we're going to look at motion graphs. First, we're going to look at the graph of position versus time. The graph of position versus time. So let's put the position on the vertical axis and time on the horizontal axis like this. So this is what you call motion graph. So let's say the graph of the position versus time for a certain particle looks something like this, okay? And let's say we want to find the average velocity between these 2 points, all right? So let's say this is initial time over here. This is final time over here. This is going to be initial position, and this is going to be final position, okay? Now, let's look at the definition of average velocity. Average velocity, by definition, is x final minus x initial divided by t final minus t initial. Now look at the graph. This interval over here is t final minus t initial. And this interval over here is x final minus x initial. Now this is vertical change, this is horizontal change. The ratio between the vertical change and the horizontal change is the slope of the straight line joining these 2 points over here, okay? So you can say that average velocity can be obtained from a graph of position versus time at the slope of the line joining the 2 events, okay? So by definition, average velocity is change in position divided by change in time. So if you look at the graph, the ratio between change in position and change in time is vertical increase divided by horizontal change over here, which is defined to be slope in math, okay? So you can say that average velocity can be obtained from a graph of position versus time at the slope of the line joining the 2 events. So the conclusion is average velocity can be obtained from the graph of position versus time at the slope of the line joining the 2 events. The line joining the 2 events. All right, the 2 events. All right, now let's look at instantaneous velocity. Instantaneous velocity, if you remember, is average velocity measured a very, very small interval of time, okay? So if you keep pushing this final time towards the initial time, you see, if over here, of this line over here, if you get closer of this line, eventually, as the difference tf minus t approaches 0, is going to be the slope of the line touching the point, touching the curve at one point, which is the tangent line. So the conclusion is instantaneous velocity can be obtained from the graph of position versus time at the slope of the line tangent the curve at the given point, okay? To find instantaneous velocity from a graph of position versus time at a certain point, you simply find the tangent line, which is the line touching the graph at one point, and you measure the slope of that line. That'll give instantaneous velocity. So the conclusion is instantaneous velocity is the limiting value of this one. You take delta x over delta t, and then you push delta t to 0, okay? Graphically, instantaneous velocity can be obtained as the slope of the line tangent to the curve, tangent to the curve at the given point, So average velocity is the slope of the line joining the two events, but for instantaneous velocity, the two times have to be very, very close to each other. That is, as the difference time approaches 0, the line basically becomes a line touching the graph at one point, which is the tangent line. So instantaneous velocity can be obtained from the graph of position versus time as the slope of the line tangents the curve at the given point. Now let's look at the graph of velocity versus time. The graph of velocity versus time. Let's put the velocity on the vertical axis. This will be the velocity, and this will be the time. Okay. Suppose the curve of velocity versus time looks something like this. Okay. And we're trying to find the average acceleration in these 2 points. Okay, so you've got this is the initial time. This one over here is the final time, and then this would be the initial velocity, and this would be the final velocity. Okay, so by definition, average acceleration is v final minus t initial divided by t final, v initial, and then t final minus t initial. Okay, now let's look at these differences. T final minus t initial is this interval over here. Okay, this over here, and v final minus v initial is this interval over here, vf minus vi. Okay, so according to this graph, average acceleration is the ratio between the vertical change over here and the horizontal change over here. But as you know, the ratio between vertical change and horizontal change is the slope of the line joining the two events. Okay, so you can say that average acceleration can be obtained from a graph of velocity versus time at the slope of the line joining the two events. Okay, so the conclusion is average acceleration can be obtained from the graph of velocity versus time, as the slope of the line joining the two events, Okay, so to get average acceleration from a graph of velocity versus time, all it is, you connect these 2 points, the straight line over here, and the slope of that line gives you the average of the acceleration in this time interval. Okay, next let's look at instantaneous acceleration. Instantaneous acceleration is you take the ratio between delta v and delta t, which is average acceleration, and then you take the limit of this as delta t approaches 0. That gives you instantaneous acceleration. In other words, you bring these 2 times closer and closer to each other, so the difference is close to 0. Let's keep pushing this towards ti. Okay, so you get this line, when you put over here with this line, so eventually as delta t at this time difference approaches 0, this line would be a line touching the curve at 1 point, okay, which is the tangent line. So we can say that instantaneous acceleration can be obtained from the graph of velocity versus time at the slope of the line tangent to the curve. So you can say that instantaneous acceleration can be obtained as the slope of the line tangent to the curve at the given point, Okay, so to get instantaneous acceleration from a graph of velocity versus time, all it is, you draw the tangent line at the given point, which is a line touching the curve at one point, then the slope of that line would give you instantaneous acceleration. And if you want to find the average acceleration in a certain time interval, all it is, you connect those 2 points, the initial point and the final point in the velocity versus time curve, and then you find the slope of that line. That'll give you the average acceleration in that interval. Okay, next let's see how we can get displacement from a graph of velocity versus time. Okay, let's look at displacement. Let's start from an easier situation. Let's say the velocity is a constant like this. Okay, this is the velocity, this time over here. All right, but we know that displacement delta x, well, if this is a constant, then instantaneous and average velocity will be the same. So you got delta x equals average velocity times time, because average velocity is displacement divided by time. Okay, now this is time, this over here is the average velocity v bar. Okay, if you take the product of this, which is average velocity, and this one, the time, you get the area of this curve over here. Okay, that's the area of the rectangle. If you take the product of the velocity and the time, you get the area of this rectangle. So even though this is for the case where the velocity is constant, this applies for any kind of a curve. If you have a graph that looks something like this, this velocity, this is time, then the displacement will simply be the graph between the graph of velocity versus time and the time axis. Okay, so we can say that displacement can be obtained from the graph of velocity versus time as the area enclosed between the velocity versus time curve, between the velocity versus time curve and the time axis So you see this is the velocity versus time curve, and you take the area enclosed between this axis, the time axis, and this curve over here. This area over here is equal to the displacement. Okay, now you see in this case positive velocity means it's moving to the right. Okay, so if it's moving to the right, displacement is positive. Okay, how about if you have something like this? Let's say the curve is like this. Okay, so this means the velocity is negative. Negative velocity means the particle is moving to the left. So that tells you this area should be negative. Okay, it's moving to the left, the displacement will be negative. So areas above the time axis are taken to be positive, while areas below the time axis are taken to be negative. Because if the area is below the time axis, it means the velocity is negative, and that also makes the displacement negative because it's moving to the left. Okay, so areas above the time axis are taken to be positive, while areas below the time axis are taken to be negative. All right. Now we're going to look at some examples. Let's have a graph. Let's say this is our graph. Let's say it's 1, 2, 3, 4, 5, and so on. And this is 1, 2, 3, 4, maybe -1, -2, -3, -4. Okay, suppose we have the following graph. Suppose it goes well, let's say this is 1 over here, this one 2. Anyway, let's say this is 3 over here. So let's say it goes over here like this, and then it starts decreasing like this, and then it goes like this, let's say. So this one over here is 2, this one is 3, and this point over here is also 3. All right, so now let's ask some questions. Number 1, so this is the position and this is time over here. Okay, so this is a position versus time curve. All right, let's say calculate the average velocity between, let's say, t equals 0 and t equals maybe 3. Okay, so at t equals 0, the particle is here over here. Okay, and at t equals 3, the particle is over here. Okay, so average velocity is the slope of the line joining the 2 points. Okay, so it's going to be the slope of this line over here. Or you can do it this way. Average velocity is x final minus x initial divided by t final minus t initial. Okay, so the initial point ti xi is this point over here, which is 0, 3. Okay, so this is 0, 3, and the final point, which is t final, x final is over here, which is its x is 3 and its x value is 0. Okay, so using these numbers, x final minus x initial is 0 minus 3, t final, which is this one, minus t initial is 3 minus 0. Okay, that'll give you -1 meters per second. Okay, so as you can see, it's negative because the line is inclined in this direction. If a line goes from this quadrant to this quadrant, the slope is positive, but if the line is inclined this way, it will be negative. All right. Number 2, calculate the displacement let's say between maybe t equals 2 and t equals 5. Okay, so we want to find the displacement between this point and this point over here. All right, so remember, we're looking for this one. Delta x is x final minus x initial, so we're just looking at the positions. Okay, so the x initial is over here, you see, which is 3. So we've got x initial is 3 and x final is over here. This is x final, which is -2. X final is -2, so the displacement is x final -2 minus x initial minus 3, which is negative 5 meters, which means the particle displaced to the left. Okay, it was displaced from here to this location, so it's displaced by 5 units to the left. Now let's calculate the instantaneous acceleration at, let's say, t equals 3 seconds, let's say. Okay, so we want to find instantaneous acceleration at this location over here. If you remember, instantaneous acceleration is obtained from a graph of position versus time at the slope of the line tangent the curve. But if the curve is a straight line, then the tangent line is the line itself. Okay, so basically in this case we calculate the slope of this line. Okay, so we can take these 2 points to get the slope of this line. Okay, so you can say instantaneous acceleration in this case equals average acceleration, because the graph is a straight line. Okay, so it'll be I mean instantaneous velocity, I'm sorry, velocity, instantaneous velocity. We're talking the graph of position versus time. So instantaneous velocity at t equals 3 seconds. So we're looking at the instantaneous velocity at this point. The instantaneous velocity is obtained as the slope of this line, but for straight line the tangent line is the line itself. So basically we have to calculate the slope of this line, that is horizontal change divided by vertical change. So in this case the initial point ti xi, okay, this is our initial point over here, which is 2, 3, and then our final point for this line, if you take this line over here, is negative, the time is, well, let's say 3, is somewhere over here. Okay, maybe let's say it's 3.5. Okay, let's say the time is, or alternatively we can use these 2 points. It doesn't matter the slope of the line. So let's take these 2 points over here. So the initial point is, for this one, still 2 and 3, and the final point will be 3, 0. Okay, so we have t final, x final, the time is 3, and the position is 0. Okay, we're trying to calculate the slope of that line. All right, so in this case the instantaneous velocity equals the average velocity, because it's a straight line. So we have xf minus xi minus tf minus ti. Okay, so this is the final time, 0 minus 3, and the time is the final minus the initial 2. Okay, so you've got negative 3 or 1, that is negative 3 meters per second. All right. Okay, number 4, let's say at what intervals of time is the particle at rest. Okay, so we're looking the intervals for which the particle is not moving. Basically we're looking for the points where the position is not changing. Okay, so you see, if you look at this interval, the position remains 3. The particle is at rest at x equals 3 over here, so it's not moving. So one of the intervals is from 0 to 2. Okay, the other interval is this one over here. It's not moving over here too. Let's say this time is 3.5 over here. Okay, so the intervals are from 0 to 2 and from 3.5 to 5. from t equals 0 to t equals 2, from t equals 0 to t equals 2, and from t equals 3.5 to t equals 5. All right? So these are the two intervals where the particles are moving. But over here, you see the position is changing and it's moving to the left. All right. Next, we're going to look at the graph of velocity versus time. The graph of velocity versus time. Velocity versus time. Okay, so let's take a graph like this. So it's 1, 2, 3, maybe 4, 5, 1, 2, 3, -1, -2, -3. Okay. Suppose this is a graph. It goes like this, and then it remains horizontal until t equals 4, and then comes back this way. Maybe it goes a little farther. Say 6, and then stops over here. Let's say this point over here is 6, this is 7, this is 8 over here, let's say. Okay, so let's ask some questions. A, what is the initial velocity? What is the initial velocity? Now remember, in this case, the graph is velocity versus time, okay? So velocity is the value of the vertical axis. So being asked for the velocity at t equals 0 is basically 0. The value of velocity at this point is 0. So the initial velocity for this motion is 0. The particle is starting from the rest. Now let's say calculate the average acceleration, for the entire trip, okay? So that means starting from this point to this point over here, okay? So we're looking for average acceleration. Average acceleration is v final minus v initial divided by t final minus t initial. If you want to connect these 2 points over here, these are our points, this is our final point, our initial point is the slope of the line connecting these 2 points over here, is the slope of this line over here. Okay, so you can simply calculate the slope of this line, or you can use this formula over here. Okay, so the ti bi, that is this point over here, because they're being asked for the entire trip, is 0, 0. Time is 0, speed is 0, because 0, 0 over here. And the final point over here, that is t final and v final, the time is 8, and the velocity is -1. Okay, so using this formula, vf minus vi is -1 minus 0, and tf minus ti is 8 minus 0. So you get -1 over 8 meters per second. Okay. Now let's calculate the instantaneous velocity at t equals 5. Instantaneous acceleration at t equals 5. Okay, so we're looking at the instantaneous acceleration at this point. Instantaneous velocity, I'm talking about acceleration, I'm sorry, instantaneous acceleration. Okay, so we're looking at the instantaneous acceleration at this point over here. And the instantaneous acceleration is the slope of the line tangent to the curve, okay? But this is a straight line, so the tangent line is the line itself, right? So basically, it's going to be the slope of this line. In other words, the acceleration is a constant variable, so average and instantaneous are going to be the same, okay? So we can take any 2 points in this line to calculate the instantaneous acceleration. The acceleration is a constant on this line because the graph is a straight line, so the average and the instantaneous are the same on this curve, okay? So we can use any 2 points. Maybe we can use these 2 points over here to calculate the slope of this line, okay? So in this case, we have instantaneous acceleration equals A average, that is V final minus V initial divided by T final minus T initial, okay? And the points are, if I take this point over here, it is 4, 2. So let's say TI VI would be this point over here, which is 4, 2, 4, 2. And then if I take TFB final, if I take my final point to be this point over here, that is 5, 0, 5, 0. Okay, so using this formula, A equals VF minus VI divided by TF minus TI, we get V final is 0, V initial is 2, T final is 5, and T initial is 4. So you get negative 2 over 1 or negative 2 meters per second squared. All right. Now let's say, at what intervals of time is it accelerating? At what intervals of time is it accelerating? Remember, acceleration means an increase of velocity. So it's, you see on this interval, the velocity is increasing, right? And on this interval it's decreasing. So it is accelerating on the interval 0 to 2. So the answer for this one is t equals 0 to t equals 2. Okay? At what interval is it decelerating? Remember, deceleration means decrease in velocity, so it's decreasing over here. So it'll be from t to 4, maybe from t equals 4 to t equals 6. So this would be from t equals 4 to t equals 6. And at what interval of time is it not accelerating, or is it moving with a constant velocity? Is moving with a constant velocity, or with acceleration 0. Okay, so you see this is a velocity axis, so it's constant over here and over here. So it's from t equals 2 to t equals 4, and from 6 to 8. So this is from t equals 2 to t equals 4, and t equals 6 to t equals 8. Okay, these are the two intervals where the particle is not changing its velocity, where the acceleration is 0. In other words, the slope of this line is 0, so acceleration is 0, which means the velocity is not changing. The same thing over here. The slope horizontal line is 0, so acceleration is 0 over here, and the particle is not moving. Okay? Now, let's obtain displacement. Number 6, let's say calculate the displacement of the particle, let's say between t equals 0 and t equals 4. Okay, so we want to calculate the displacement from here to here. If you remember, displacement can be obtained from a graph of velocity versus time, as the area enclosed with the graph of velocity versus time and the time axis. So basically we have to calculate this area over here to get the displacement between t equals 0 and t equals 4. Okay, so we can divide this in two parts. So we can find the area of this one first, and then the area of this one, and then add them together. Okay, so I'm going to divide this into a triangle and a rectangle. So delta x, we can say, so delta x would be the area of the rectangle, the triangle. Now the base of this triangle over here is 2, and the height is 2. Okay, so we have 2 over here, and then plus the area of the rectangle. You see, for this rectangle, the base is 2, from 2 to 4, and the height also 2. Okay, so we have 2 over here, 2 over here. Well, the picture is exaggerated, but they're both equal. So this is half of base times height, okay, for the triangle, 2 times 2. And then this is the triangle, 2 times 2. Okay, so you get 2 plus 4, 6 meters would be the displacement in this interval. Okay, so displacement is obtained at the area enclosed between the velocity versus time curve and the time axis. So between t equals 0 and t equals 4, we're looking at this area. Okay, we can divide this area as the area of a triangle and the area of a rectangle. Okay, so this is base is 2, height is 2, so the area is going to be half of 2 times 2, which is 2. And then for this one, you have base 2 and height 2, 2 times 2 is 4, 4 plus 2 is 6. Okay, now let's calculate the displacement between t equals 4 and 2 equals 8. Okay, number 7, calculate the displacement between t equals 4 and t equals 8. Okay, so we want to calculate this displacement over here from here to here. Okay, so you see, now remember, areas above the time axis are taken to be positive, so this is going to be positive, but areas below the t-axis are taken to be negative. The reason is, on this region above the t-axis, the velocity is positive. It means it's moving to the right, which makes positive. But on this range over here, the velocity is negative, which means it's moving to the left, and that gives you negative displacement. So the displacement is this area minus this area over here. Okay, so we're going to divide this into 3 parts: this one, this one, and this one. All right, so we're going to say, no, we're looking at this area over here, this area over here. We're going from t equals 4 to t equals 8. Okay, So we're going to divide this into 3 rectangles. So we're going to say displacement equals the area of this rectangle first, this one over here. I'm going to write a triangle. This triangle, its base is 1. Diagram is exaggerated, but this is 1 from 4 to 5, and the height is 2. Okay, so we've got 2 over here. And then we're going to take the, now remember, now it's minus, it's below the time axis, and that is this rectangle over here. Okay, its base is 1, this one is 1, and its height is also 1 from here to here. Okay, 1. So we have 1 over here, and then we have the rectangle. We're also going to subtract that because it's below the t-axis, and that is a triangle of base 2. Okay, this is 8 over here, and height 1. So you've got this rectangle, its height is 1, its base is 2. Okay, so the displacement is, this one is above the t-axis, and that is half of 2 times 2. Okay, that is the area of this times 1, I'm sorry. This is, its height is 1, its base is 1, so it'll be times 1 over here. Okay, and then minus the area of this, which is half 1 times 1, minus the area of this one, which is 1 times 2. Okay, so we have 1 over here minus half minus 2. Okay, so that's half, this is half, minus 2 is negative 3 over 2. So you see, the displacement is negative 3 over 2, or negative 1.5 meters, which means displacement to the left. So remember, when calculating displacement, the displacement above the t-axis, this area over here, is saying positive because the velocity is positive over here. It means the particle is moving to the right. That makes the displacement positive. But below the t-axis, the velocity is negative, which means the particle is moving to the left, which makes the displacement negative. So areas below the t-axis should be negative, and areas above the t-axis should be positive.